Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the first module of this course, that is the introduction module. And the idea behind this module is to give you a basic introduction to operating systems. So within the first module, we are on the third topic, that is the compute stack. So we have already discussed at the beginning of this topic what is a compute stack. Basically, the computer system has a layered architecture, and we have already seen what are those layers in the first video, right? And in the previous video, we talked about the computer hardware, that is the bottommost layer in the computer stack. So basically, we discussed about what are the major components in the computer hardware and how do they work. And also we saw what is the interface that the computer hardware exposes to the layers of software above. Now in this video, we are going to discuss the software that is responsible for managing the computer hardware, that is the operating system. So we have already talked about operating system in great detail in a set of videos in the previous topic. So the way we are going to do this video, we are just going to recall all the concepts that we studied in that topic and bring them in one place. So without further ado, let's get started. So this is the compute stack, and at the very bottom you can see this is the computer hardware, and this is the hardware interface that is exposed to the layers of software above. So as you can see, the user applications do not run directly on the hardware interface, and the reason being that the hardware interface is too complex to program, right? So first of all, this interface has to be simplified, and that is why we have some layers of software between the user applications and the hardware. And the first layer is the operating system. So the operating system is basically the first layer that runs on the hardware. We often say that the operating system runs on bare metal, directly on the hardware interface. And the fundamental responsibility of the operating system is to manage this computer hardware. So when it comes to managing the computer hardware, there are two major roles that the operating system has to play. The first one is to make sure that the hardware is easy to use, and the second one is to ensure that the computer hardware is used efficiently. So let us see how the operating system makes the hardware easy to use. It does this by the concept of abstraction. So what is an abstraction? So basically there are several computer hardware resources in the system. For example, CPU, memory, and IO devices. What the operating system does is that it takes each physical resource and transforms it into a virtual resource. And this virtual resource is much easier to use and much more powerful, right? This transformation from a physical resource to a virtual resource is the idea behind abstraction. We can say that that virtual resource is an abstraction over the physical resource. And we have seen many such examples of abstraction. For example, for CPU, the abstraction provided is that of a process. For memory, the abstraction is the address space. And for IO devices, the abstraction that operating system provides is of files and directories. So we have already seen these abstractions in the previous topic, and we will recall each of them in this one also. So the next role that the operating system plays when it comes to managing the computer hardware is to ensure that the hardware is used efficiently. And as you can see, there are several resources in the computer system. There is the CPU, memory, and IO devices. And all of these resources are required by the computer applications to execute, right? So these resources are shared between all the computer applications, and they are limited in nature. We don't have unlimited compute power or memory storage. So it is the fundamental responsibility of the operating system to keep track of all these resources and properly allocate these resources to the computer applications, right? So this is how it makes sure that these resources are used efficiently. So now that we have discussed the responsibilities of the operating system, let us see how the operating system manages each piece of computer hardware. So we studied about the hardware in the previous lecture. Let us just recall the hardware interface. So this is how the hardware looks like. And the hardware interface that is exposed looks something like this, right? So the operating system has to work with this interface and simplify this. So now what we will do, we will take each of these computer hardware resources one by one and see how the operating system manages them. And we'll start with the CPU. So now let us look at how the operating system manages the CPU. So this is how the hardware interface looks like for the CPU. And the hardware interface basically says that the CPU is a collection of registers. So basically the execution circuit that is part of the CPU, that is not visible to the operating system. From the operating system's perspective, it can only see the CPU as a set of registers, right? And the way to communicate with the CPU is to read or write these registers. So this was about the hardware interface. Now let us look at what the operating system does to manage the CPU. So the underlying challenge with using the CPU is that in modern computer systems, the amount of programs that we want to run is way more than the number of CPUs that are there in the system. So as you can see in this simple example, there are n programs that want to run and there is one single CPU in the system. So how can these programs run on the CPU? The way to solve this problem is to share the CPU time between all these programs, right? So what will happen is that the CPU will be allocated to some program, and after that program has executed instructions for some time, then the control of the CPU will be given to some other program. And in this way, the control of the CPU will be frequently switched between all the programs, and that is how all these programs can make progress by executing instructions for some brief amount of time. And this concept is called time sharing, right? And who implements this time sharing? Basically, it is the operating system. So in order to implement the time sharing, the operating system first of all has to keep track of all the running programs in the system. And as we already discussed in the previous topic, this concept of running program is called a process. This is an abstraction. So a process is a running program, and it is the responsibility of the operating system to keep track of all the processes in the system and ensure that each process gets a fraction of the CPU time so that it can execute instructions and make progress. So you see, this is what makes the CPU easy to use. Now, as a user, we don't have to worry about whether the CPU is available or not. All we have to do is go ahead and launch a program. And when that program is running, it is a process from the operating system's perspective, and the operating system will ensure that that process gets a fraction of the CPU time. So now as users, whenever we want to use the CPU, we don't think in terms of CPU, we think in terms of launching programs, right? And these programs are called process. So the interface, you see, this is the hardware interface, and over this interface, the operating system has created an abstraction that is of a process. So this is how we think of when we want to use the CPU. We think in terms of processes, right? So this is how the operating system manages the CPU and makes it easy to use. Now let us look at the memory. So now after talking about the CPU, let's look at the memory. So this is the hardware interface that is exposed by the memory. So from the operating system's perspective, the memory is a sequence of bytes, and each of these bytes has a unique address. And the way to interact with the memory is to perform read or write. So the operating system basically can issue a read transaction saying that given this address, give me this data, or the other way is to write. So basically now you can give an address along with the data and say write this data at this address. So this is how via read or write or load or store the interaction with the memory happens, right? And now we'll look at how the operating system manages this memory. So what the OS does in the context of the memory is that it provides an illusion of a private memory for each process in the system. So in this computer, let's take a hypothetical example. There are three processes A, B, and C. For every process in the system, the OS provides the illusion of a private memory. So let us see how does that work. So basically, the illusion of private memory is created by the abstraction of an address space. So what is an address space? So this is the physical memory, right? And with every memory location, there is an address associated. So an address space is basically the collection of all these addresses. So this is the physical address space, right? So the physical memory has 16 locations, and the set of addresses from 0 to 15 makes up the physical address space, right? So now what the operating system does is that it forbids all the processes from accessing the physical address space directly. So then how will the processes access their data? To do that, the operating system now creates private virtual address spaces. So you can see there are three virtual address spaces, one for each process. And now the process can only access its own virtual address space. And as you can see, every address in the virtual address space is mapped to some physical address. And as you can see, if the process accesses some virtual address, and after the translation has been done from virtual address to physical address, it can access its data that is present in the memory. So you can see the way the mappings have been done. Process A can only access its own data. Similarly, process B can only access the data that is part of process B. So now you see how this illusion of private memory works. So these virtual address spaces kind of create a view, a subset of the physical memory, that is the data that is part of that process, only that is visible to the process. So this is how the virtual memory looks like. As you can see, each process can only access its own data, and that is why it feels that the memory is private to it. But in reality, the memory is completely shared between all the processes in the system. There is nothing shared about the memory, right? So this is how the concept of virtual memory works. And one point is that this virtual memory is only an illusion. There is no separate memory here. There are only address spaces. The way the mappings have been done between these two address spaces, it creates an illusion of a virtual memory, right? So now let us see some benefits of virtual memory. So the first major benefit of virtual memory is isolation. So as you can see, each process can only access its own data, right? Although the physical memory is shared between all the processes, the physical memory contains data for all the processes, but the restriction is that any process can only access its own data, and this has been this isolation or protection has been enabled by the virtual memory. So this is one of the most important benefits of virtual memory. Now let's discuss the second benefit. So as you can see in this diagram, we have assumed that the data for a process would always be neatly arranged in a continuous fashion like this, but this is not necessary, right? So the data can be arranged in any format. So as you can see in this case, the data is all scattered. But since the virtual address space has been decoupled from the physical address space, using the virtual address space, we can still provide the illusion of a continuous memory. So as you can see, even though the mappings are like this, these addresses are continuous and they will lead to the data in the physical memory, and so the view that the memory is continuous is still maintained, right? So this is one of the another benefits. So as a programmer, now you are given the illusion that the memory is always arranged continuously, although this might not be the case. So you can see all the virtual address spaces are continuous, but the physical memory is totally scattered, right? So this continuity is another benefit of virtual memory. And the final benefit of virtual memory is that consistency. So no matter how the physical memory is arranged, we have the same view of the virtual memory, right? We just saw this. So this consistency is very important as a programmer. You don't want to worry about where your data is. So the the layout of the memory can change altogether. This can be arranged in some different fashion, but no matter how the physical memory is arranged, how your data is present in the physical memory, you as a programmer is always provided this consistent view of the memory. So this is very important. So there is isolation, there is continuity, and there is this consistency. So now as a programmer, you have a very simple view of the memory, right? So this is how the operating system manages the memory and makes it easy to use. So another important point is that the operating system not only provides the illusion of a private memory, it also provides the illusion that the memory is huge. So for every process, what the operating system does is that it just increases the size of the virtual address space, right? So as you can see, if you combine these three virtual address space, then the amount of physical memory required to back these virtual address spaces is much more than the size of the physical memory. And now the operating system basically leverages the persistent storage or the disk. So what it does is that it stores whatever is possible in the physical memory. So for example, for process A, some of the virtual addresses are mapped to physical memory and the rest of that is mapped to the disk. So it is now leveraging both the physical memory and the persistent storage to map these virtual addresses, right? So this is how, by using the persistent storage, the operating system is able to provide the illusion that the amount of memory in the system is huge. So for every process, now the virtual address or the virtual memory is quite large, and now as a programmer, you are provided that the memory is private to you and it is very large. So this is how now as a programmer, the memory becomes very easy to use. So now we saw how the operating system basically takes this simple hardware interface and provides the abstraction of an address space over this memory to create the illusion of a private and very large memory for all the processes. So this is what makes the memory easy to use. So this is how the operating system has managed the memory. Now let us talk about the IO devices. So now let us see how the operating system manages the IO devices. So this is the interface of IO devices. So for every IO device, there is a device controller, and within the interface of the device controller, there are some registers with which the operating system communicates. So basically, the operating system can communicate with these registers to give some command to the device controller, which will then execute that with the device. So basically, from the operating system's perspective, an IO device appears as a set of registers because it is only these set of registers in the device controller interface with which the operating system can interact. the operating system cannot directly interact with the device. It has to go through the device controller interface. So as you can see, this is a set of registers, and as I said, for the operating system, the IO device appears as a set of registers, and since there are multiple IO devices, this picture shows the same. So now that we have understood the interface, the hardware interface of the IO devices, let us now look at what does the operating system do to manage them. So now let us understand what is the challenge with using the IO devices. So here we have a simple system with a few IO devices. This is the disk, this is USB stick, this is CD-ROM, keyboard and mouse. And with every device, we have a piece of hardware called the device controller that is responsible for managing that device. So as you can see, for the disk, we have the disk controller, for the USB stick, we have the USB controller and so on. Now this device controller is basically very unique to the device that it is managing. So a disk controller cannot manage any other device. It has been designed to manage the disk, and hence the set of registers that are part of the device controller interface that are also very unique. So basically what I'm trying to say, this device controller interface is very unique, right? So no two device controller interface are same. And now this is a problem. Why? Because let's take the example of these three devices. All of these are storage devices, and they are used to store data persistently. Now imagine writing a program to read or write data from these storage devices. You will have to deal with three different interfaces for doing the same thing, and this is very non-intuitive and not user friendly. So what the operating system does, first of all, it basically identifies common types of devices. So these three devices are more similar. They are all storage devices, and they store data as a sequence of blocks. So they are block oriented devices, and these two devices are more similar to each other. So these the keyboard and the mouse are used by the user to provide input, and the input data comes as a stream of characters. It's a character stream. So these are character oriented devices, right? So the operating system has more device classes, but for this example, these two classes are sufficient: the block oriented devices and the character oriented devices, right? So now what the operating system does, for the same device class, it defines a unique interface. So for the block oriented device, it has defined a unique interface, and for the character oriented device, it has defined another device class interface. And now all these devices have to conform to this interface. So this is where the device driver comes into the picture. With every device, there is a device controller and also a piece of software called the device driver, and it is the responsibility of the device driver to bridge the gap between this controller's interface and the uniform interface that the operating system has defined. So as you can see, now every device comes with a device driver. So these block oriented devices will first of all be brought to a same uniform level. So this is the uniform level for block oriented devices. And similarly, the keyboard driver and the mouse driver first of all bring this character oriented devices to a uniform level. So by first of all bringing uniformity to the interface of the devices, the operating system has made it much simpler to use these devices. So now let us see what else does the operating system do in the context of IO devices. So let us see how the operating system simplifies the usage of IO devices further. So let's take the example of storage devices. As we already know, storage devices are a sequence of blocks, and we have three different storage devices, right? And this is the device controller interface level. So you can see for every device we have a different block structure. The number of blocks and the size of blocks is very different for different devices. So what we have done, we have used the device drivers. The device drivers will basically bridge the gap between these different interfaces and bring them to a common uniform interface. So this is how the uniform interface looks like. Now you can see the block structure is same. The size of the blocks is same. So all of the storage devices have now at least been brought to a uniform level. Although this interface is simpler than the previous one, but it is still too complex. Why? Because if you want to read or write data from this interface, then you have to deal with block addresses. So basically you need to remember where your data was. So dealing with block addresses is non-intuitive and not user friendly. So what the operating system does, it simplifies this further by providing an abstraction. So that abstraction is that of a file. So what the operating system says, put all of your related data into one logical unit and give it a name, and I will map those files into the blocks. So you can see we have three different files. One is a text file, the next one is an image, and one is a video file. We could have many other file formats. So all of the related data have been put into one logical place, right? One unit, and that is a file. And the operating system is mapping these files to the block addresses, right? So now you don't have to deal with block addresses. And not just this, there are special types of files called directories, and using directories you can even organize your files, related files, into one directory, right? So this organization is also very useful. So using this abstraction of files and directories, you see how the operating system has made using these storage devices much more simpler. So not only we need device drivers, we also need the abstraction of the file over these drivers to make the storage devices easy to use. So the next point is that the files are not only used to store data on these storage devices, it is also used to model all other IO devices. So all other IO devices are represented by special files. So let's take the example of Unix operating system. In the Unix operating system, the keyboard is the standard input, right? It is expecting the input to come from the keyboard, and the display is the standard output. So basically what the Unix operating system does is that it represents the keyboard by a standard input file. So whatever characters that the user will type, that will be stored in this standard input file, and any other process can read this file to get the data of the keyboard. Similarly, the display is represented by the standard output and standard error files. So whatever data any process wants to display on the monitor, they will put it in the standard output file or the standard error file, and the contents of these files will be displayed on the console or the monitor. So this is how files are not just used to store data on the storage devices, they are also used to model IO devices. So now this is how the interface looks like. So this was the hardware interface. So now the operating system has provided the abstraction of files to represent IO devices. So now we think of IO devices in terms of files and directories. This is how the operating system manages the IO devices. So this is how the interface of the OS looks like finally. So what the OS has done, for every physical resource in the system, it has provided an easy to use abstraction. So for CPU we have the process, for memory we have the address space, and for IO devices we have the files and directories. So to summarize what we have learned, so these are the hardware components, right? And in the previous video we looked at the hardware interface. So this is how the hardware interface looks like for each of these components. And in this video we have seen how the operating system provides an abstraction for each of these components, and this is how the simpler interface of the OS looks like. So there is the process, address space, and files and directories. So this is how the interface of the OS looks like. So now what we will do, we'll spend some time and understand how we can use this interface. And this interface is called the system call interface. So let us spend some time and study the system call interface. So let us look at the system call interface in some more detail. So if you look closely, what the OS has done, it has taken each physical resource and provided a virtual resource for it. So these virtual resources are basically an abstraction over the physical resource. So now what has happened, the same machine has now two views. So this is the hardware interface, this is the real view of the machine. But now what the OS has done, by providing this set of virtual resources, it has created a new view of the same machine, and this view of the machine or interface of the machine is much more easier to use and also much more powerful. So that is why we sometimes say that the OS takes the real machine and kind of builds a virtual machine on top of the real one. So this is how the system call interface, you can think of it as, you can think of the system call interface as the interface to some virtual machine, which is easy and much more powerful to use than the real hardware, right? So as we said that the OS creates a virtual machine over the real one by providing a set of virtual resources. So it must also provide a way in which we can perform operations or use these virtual resources. So for example, if you talk about a process, then we must have a way to create a process, terminate a process, pause it or resume it, right? So there could be many more operations that could be defined. For memory, if you say some example operations are allocation, deallocation. For files, some example operations are opening a file, closing it, then reading data from it, and then writing to it, right? So the point is there are several virtual resources that the OS has created. Now it must also provide a mechanism so that the layers of software that run on top of the OS can use these virtual resources. So this is where system calls come into the picture. So basically for every operation that can be done on a virtual resource, the OS provides a system call. And a system call is just like a function or routine. So whenever you want to perform an operation on one of these virtual resources, you can invoke this system calls just like functions. So some example system calls are listed here. I won't go into the detail of it. So we will study system calls in later videos in great detail. So just to give you some examples, this is a fork system call, and fork and exec are used for the creation of processes. Wait is used to wait on an existing process. Exit is used for termination, right? So basically for every operation that we said that we want, you can see the OS has provided the system calls. And for similarly, for memory, we have mmap, brk, and sbrk. So these are used for allocation, deallocation of memory. Finally, similarly for the files, we have open, close, read, and write, equivalent for the every operation that we saw: opening a file, closing it, reading, and writing. So basically now we have a set of system calls corresponding to each of the operation that we can perform on these virtual resources. These system calls are provided by the OS and defined inside the OS's code. So here you can see an example of a system call. This is the read system call, which is for reading data from a file. So you can see it looks just like a function call, right? So it takes some arguments. For example, this is the file descriptor, and this is the buffer where you want to read the data, and this is the number of bytes that we want to read from the file. And after this operation is completed, it returns the number of bytes that it has read. So a system call looks just like a function call, but there is a difference. So what is the difference? Basically, a system call transfers control to the operating system, right? So a normal function call, if you think about it, when we execute a normal function call, the control will remain within the user application. But when you execute a system call, the control is transferred to a well-defined routine in the operating system. This is where the operation that is being requested will be serviced by the operating system. So this is the basic difference between a system call and a normal function call, right? So as we know that for every operation that we can perform on these virtual resources or abstraction, the OS will provide a system call. So the system call interface contains a bunch of them, right? So from the user applications perspective, the system call interface looks like this. And you can say from the user applications perspective, the OS is a library of system call. Whenever it wants to perform any operation on any virtual resource, it will invoke one of these. So this is how the system call interface looks like. So we are done with the operating system. We looked at what are the major responsibilities that the OS performs, and we saw how the operating system takes each physical resource and transforms it to a virtual resource or an abstraction. And finally, we looked at this interface that is exposes to the layers of software above, that is called the system call interface. So guys, this was it for this video. Thank you very much for watching, and I'll see you in the next video. Thank you.